Now you might think, well, Bill, if the star in the name of the type declares or represents the type of variable, yes, it does. It's exactly what it's going to do. It's there to store the address. That means that any time a type starts with a star, we're talking about a variable who's going to have 4 to 8 bytes of memory allocation, depending on the architecture. On the playground, 4. On your local machine, 8. Yes, that's exactly right. We're going to pass an address across this program boundary. We need to store the address. We need enough memory to store that address. 32-bit address, 4 bytes, 64-bit address, 8 bytes. Well, Bill, if the star in the type's name dictates the variable itself and its allocation, then why can't we just declare the star by itself? And we simply can't do that for one reason. You see, we passed the address of count across the program boundary. We can now say that this inc variable sitting on the stack frame for the increment function points to this 4 bytes of memory right here allocated on the stack frame for main. We've now shared it. But here's the thing. Sharing alone isn't enough. The whole point of sharing is so we can read and write to that memory that's been shared. And we cannot read and write to memory unless we know what? The type information for that memory. And so the other part of this type is not what is being stored in inc, but what we're being shared so we can read and write to that memory with the right level of integrity. And if we look at the rest of this code, what we now see is the use of the star again in order to operate against the pointer. And this can be a point of confusion. I want you to understand that the star here in the variable declaration is not an operator. It is part of the type's name. One day, when I can, I'm going to go to the Social Security office and change my name to be Star Bill. I can do that. Star can be a character in my name. I mean, all the sports guys do it. Why can't I do it? I want you to understand that that is the name of the type. But this is really acting like an operator, just like the ampersand did. If a variable by itself means value of, and the ampersand means address of, where is the box, then what the star operator means, and it can only be applied to a pointer variable, what it means is the value that the pointer points to. The value that the pointer points to. Let's read and write to that value. And here what I'm saying is increment by 1, the value that the pointer points to, and now I get to manipulate memory outside of my own stack frame thanks to the pointer. The pointer's job is for sharing. That is its sole purpose in life. And now if I run this code, what we see again is that this is at 9FA4. There it is, 9FA4. And we can see here that our pointer variable also is at address 9F98. Brilliant, lower in the memory. But here's the kicker right here. This is the value of our pointer variable. Remember, the value of a pointer variable is always an address. Pointer variables are not special. They're variables like any other variable. They have an allocation. They store a value. It's just that all pointer variables store only one type of value, and that's an address. And look at the address that we've stored inside. It is exactly the same as the address for count. That gave us the share. And now we see that after the call to the value that the pointer points to, increment that by 1, that code on line 28, we can see here that the value of this memory location outside of our stack frame has changed. This is pointer mechanics. This is it. So we have to decide when we need to share something and when we don't. And in some later lessons, we are going to talk about value semantics and pointer semantics. This is something that a lot of Go developers miss. When do I use a pointer and when don't I use a pointer? When do I copy a value and when do I share it? When do I use value semantics and when do I use pointer semantics? And I don't blame a lot of people for being confused. If you're coming from a language like C# or Java, those languages are all about pass by reference, that you have really no control over the different semantics. You live in this one kind of semantic world. And so what Go is, because we work on the machine, we live on the machine, we have the ability to leverage the right semantic for the job that we're trying to accomplish. We're going to get much more into value semantics and pointer semantics. Value semantics mean that we're making a copy of the value as we go across these program boundaries. Pointer semantics mean that we're sharing the value as we go across these program boundaries. As we continue to learn more, I will bring up value semantics, pointer semantics. We will talk about consistency. But I want you to see right now that the pointer mechanics, okay, using pointer semantics is about sharing. Okay, let me show you another program here that's going to give us a little bit more insight about how memory works in Go. So I've got this user-defined type. It's named user. It's got name and email. And the main function has two functions here, stay on stack and escape to heap. We're going to call both of these functions from main. Now, the first function, stay on stack, is very interesting. What does it do? Well, we go ahead and we create a value of type user. Now, we know the size of a user value at compile time. We know it. It's 2 strings, right? 4 words put together. We know the size. Because we know the size, the compiler can absolutely put this user value on the stack frame for the stay on stack function. There it is. So we create this value, we initialize it, and then what do we do on line 29? If you notice, we take the value and return it. We are making a copy. Remember, everything is passed by value. So we're making a copy of this particular user value, and we're passing it back up. And back up here is going to get its own copy. Okay, brilliant. Then we can basically abandon this. We're back up here. Let me show you the next function. It looks almost identical. Look what it does. It actually does the same thing that the first function did. It creates a value of type user. It might seem that we're doing the same thing here, and we're initializing it. There we go. But there's one subtle difference. On line 39, we do not return the value itself. Notice that we are returning the address of you. That is the value that's being passed back up the call stack. Remember, pass by value means a value is always going to be copied and moved around, either the value itself or its address. There's nothing else.